In this section, we're going to take a look at stereochemistry and specifically enantiomers in more of an experimental setting. For example, the molecule I have here is called carvone, and it is a chiral molecule. And since it's chiral, it has two enantiomers, and I've drawn each of the enantiomers shown here. Now, the reality is, if you were to purchase carvone from a chemical company, well, this structure here is kind of meaningless because it doesn't tell us the stereochemistry. So we have the option of either purchasing either single enantiomer as a pure compound, in which case this first one, if you look it up, it's called plus carvone. So you can go to a chemical supplier and get pure plus carvone in a bottle. Alternatively, if you want the other enantiomer, it's called minus carvone. So we can purchase this plus or minus in pure form. Alternatively, however, you can purchase a 1-to-1 mixture of the two enantiomers. If you do so, it won't be called plus carvone, it won't be called minus carvone. That will be listed as plus minus carvone to tell you it's the mixture. And what this actually refers to is something called a racemic mixture. So if you're talking about the racemic mixture or the racemate, you're talking about a 1-to-1 mixture of the enantiomers. Now with this, where exactly do these plus and minus values come from? Well, just to give you a little bit of an idea in terms of some of the properties, these two enantiomers, you can certainly get physical properties. You can take the melting point, and they're both 25 degrees Celsius. You can get the boiling point, and they both boil at 231 degrees Celsius. So the properties of the two enantiomers are nearly identical, or they are identical so far. But there's one physical property that is different, and that has to do with the chirality of these molecules. This property is the optical rotation. We often abbreviate it as this alpha D20. The D is just the type of lamp that's used. The 20 is the temperature. And there's an instrument called a polarimeter that you can put a solution of a chiral molecule in, and it measures how the light gets rotated. And one enantiomer will rotate light clockwise. The other will rotate the plane polarized light counterclockwise. And for this particular molecule, light gets rotated 61 degrees. In the plus enantiomer, it gets rotated positive 61 degrees. In the minus enantiomer, it gets rotated to the same magnitude, just in the opposite direction, negative 61 degrees. So what we can say here is that these pure single enantiomers of chiral molecules, they're optically active. And what this special optically active term refers to is that they rotate plane polarized light. So now, if you think about the plus-minus carbone, the racemic mixture, you have a 1-to-1 mixture of the two enantiomers. So if you pass this plane polarized light through that solution, half of the molecules will rotate the light to the right. The other half of the molecules rotate it to the same magnitude to the left, and it cancels out. So in a racemic mixture, the optical rotations cancel. For that reason, the optical rotation is 0, and racemic mixtures are optically inactive.